Okay, so now we begin with the new lecture in phase equilibrium module, that is lecture number 10. So, I will just briefly recap what we did in the last lecture. So, in the last lecture we basically discussed about effect of impurity addition on stability of solutions. So, basically when you add a small amount of impurity to a pure phase, it is thermodynamically stable and mainly driven by, even though delta H of mixing can be maybe positive, the impure phases, slightly impure phases more stable because of increase in the configurational entropy, which drives the free energy of mixing to become negative in the impure phase. And then secondly, we introduced the concept of activity AI. So, you have activity is basically related to mu I. So, you have element mu I, which is equal to G I plus RT ln A I. So, this is the relation of chemical potential with respect to activity. So, higher the activity of a system, higher the chemical potential is. So, and it basically depicts the tendency of an element to leave or remain within the system. So, if the activity of a component is high, which means it does not like to stay in the solution, it wants to get out of the solution, and what that depicts is basically that delta H mixing is higher, it is positive. And when activity is lower, what it means is that the chemical potential is also lower, and the element likes to remain within the solution with the other elements, lowering the free energy of that state, and which is manifested in lower enthalpy of mixing as well. So, this is what we discussed in the last lecture. Now, we will move on to what we call as real solutions. Now, real solutions basically are different from ideal and regular solutions, because whatever we have discussed previously, they do not really describe the reality. So, previous models do not describe reality, and this is because we have not considered, we have assumed that A and B do not have size differences, but if you have two elements, they are going to have size differences. So, the factors which we did not consider first was the size. We did not consider any strain fields. When you have size differences, you will have strain, and this strain leads to enthalpy of mixing. So, these size differences and corresponding strain fields lead to changes in the enthalpy of mixing. We did not consider differences in structures, differences in crystal structure of the elements. We assume that both of them are similar structure, but they may not necessarily be the same, the structures may be different. Similarly, you can have differences in structure, not only structure, but also electronic configurations, electronegativity, and so on and so forth. So, all these differences lead, so as we saw in the structure of materials module, the formation of solid solution is governed by certain rules called as Hume-Rothery rules, which say that solid solution will form when there is a certain size difference is smaller than a certain number, when the valences of those two elements are ideally similar, or the electronegativities are similar and the structures are similar. So, these factors which were not considered in the first two models of ideal and regular solutions make the situation far more complicated, and as a result you do not necessarily form a substitution solution. Your solid solution could be interstitial solid solution, and this interstitial solid solution will have completely different free energy considerations, enthalpy of mixing for instance, as compared to regular or ideal substitutional solid solution. So, these factors were not taken into account. As a result, the solid solution and the thermodynamics associated also is different. And then we also did not consider whether two elements, we consider that both the elements will extend the solid solution all throughout, whereas in reality there could be formation of other phases. So, at certain compositions these two may react with each other and they may lead to formation of phases whose structure and properties and bonding etc., are very different from the solid solution itself. So, for instance, they may form so these phases could be for instance intermetallics, which are compounds, basically intermetallics or line compounds. They may form ordered phases, they may form various other kinds of phases. Okay. So, these kind of differences may lead to completely different situation as far as free energy considerations are concerned. So, the assumption that random arrangement of atoms will always provide a more stable structure is not necessarily true because of these differences, and actual arrangement of the atoms in such situations will be the one which yields minimum free energy with sufficient amount of entropy. So, as we know that entropy cannot be 0. So, entropy makes a very entropy. So, it is a balance between delta H mixing and entropy changes considering the differences that I just narrated that will determine the minimization of free energy. So, the possible, you may have various possible solid solutions. For instance, the ordered solid solution as we know is something like this. My apologies for the differences in sizes, but assume that sizes are same. So, hang on, let me just change the first row and make it slightly bigger. Okay. Now, here let us say the first arrangement could be like this. So, these are basically ordered substitutional solutions. You can have another scenario in which you have situations like these. And you can have some sort of clustering. Let us say few atoms here are clustered in this fashion. So, they do not have as such absolute randomness, they have some sort of clustering. So, this is, you can have a clustered solid solution. So, it is not exactly periodic because there is no ordering as such here, but atoms tend to cluster at various places. So, you can see that B atoms have clustered. So, this is, if this is B, this is A, you can see that B have clustered in different pockets, whereas A is present as well in certain different pockets. So, this is for example pocket of A, this is pocket of B, so this is pocket of B, okay. This is again a pocket of B, this is again a pocket of A. On the other hand, this is the pocket of A, this is the pocket of A. So, they have clustered each other in different regimes, and this may happen in cases where A and B do not like each other, which means AB bonds is not preferable. If you have excessive size differences, you may have completely different scenario. For instance, you may have these atoms present somewhere here, and this will lead to either a contraction. So, this is basically interstitial, and this will lead to contraction or dilation of the lattice depending upon the size difference and the size of the void. And these are basically again interstitial solid solution could again be random or ordered depending upon the enthalpy of mixing. And also this is further complicated by differences in the electronegativities as well as differences in the bonding of between different atoms. So, there are various factors which go behind defining the phase formation, what kind of solid solution will form eventually. So, let us first define the kind of phases that can form if they do not form completely random solid solution. So, in this series, the first type of solid solution, first type of mixture that we consider, so it is not solid solution as such, it is ordered phases. Now, in this class of ordered phases, there are two categories. The ordered phases are those phases in which atomic arrangement is periodically ordered. So, that we saw in crystal structures module 1, that you can have arrangement like, for instance, you can have a phase like this, so basically the manifestation of ordered solid solution is this. You have an ordered solid solution. So, you have, this is A atom, this is B atom. You can see that A and B are arranged in such a fashion, so that you can define a lattice either like this or like this, and in this you can see that if you choose this as a blue one as a unit cell, then A is at the corner and B is at the face center, and this is always the case. So, you can have either B at the corner or A at the corner, or A at the center or B at the center, depending upon which one is at the, but the pattern remains same all throughout. So, this is basically ordered solid solution. In 3-dimensional, for example, materials like so this is CuAu, so this atom is Cu and this is Al, okay, CuAl. So, this makes a structure which is periodic, but it is not a BCC lattice, it is a simple cubic, and this is what repeats itself. So, you can see that all throughout the structure, the bond that is preferred is Cu-Al bond instead of Cu-Cu or Al-Al bond, and this is because of stability of these bonds. This is because of stability of thermodynamic stability of Cu-Al bond, because the delta H mixing in such case is low. As a result, copper likes to be in close proximity with the aluminum. However, you can have a disordered form. Disordered form would be in which in the same lattice So, each atom is now 50% Cu and 50% Al. So, in such a scenario, each site is occupied, the probability of occupation of the site is 50% copper, 50% aluminum. As a result, this makes a disordered structure. Which means AA, AB and BB bonds are equally probable. In such a scenario, this makes a BCC structured lattice, but in a disordered form. So, each atom is mathematically considered as 50% copper and 50% aluminum. So, in this case, in the perfectly ordered phase, there is no Cu-Cu bond, there is no aluminum-aluminum bond, nearest neighbor as far as considered. All the bonds that are considered are Cu-Al bond. Okay. In this case, there is a possibility that you can have Cu-Cu bond, there is a possibility you can have Al-Al bond, there is a possibility you can have Cu-Al bond. So, this is, so depending upon, so now you go to generalized AB solid solution, go back to generalized AB solution, and let us say in a number of AB bonds in a completely random solution. That would be PAB, and this is nothing but Na, Z, Xa, Xb. So, Na is the Avogadro number, Z is the number of bonds per atom, Xa and Xb are atomic fraction. So, for instance, if you have, for example, if you have this as 100, this as 4, this as 0.5, this as 0.5, then PAB would be 100. Okay. But if the propensity of, if there is a propensity to, but if let us say propensity of AB bond formation, then delta H mix is less than 0. So, this says that AB bonds form more than what they would in a random solution. So, basically more AB bonds will be formed than what you will form in a random solution. In such a case, the alloy may form either short range order or long range order. And this is depicted by a parameter called as degree of ordering. And this is determined as S is equal to PAB observed minus PAB random divided by PAB maximum in an alloy divided by minus PAB random. Okay. So, basically this would be state of complete ordering. This would be random solid solution and this is the observed. So, now let us say we have a situation case 1 in which let us say we have PAB as 100, which is the observed. Total number of atoms, let us say, is equal to 100. So, in that case PAB random was equal to NA into Z into NA into Z into XA XB. So, consider NA as 100, Z as 4 bonds per atom, and if it is a equiatomic alloy, then 0.5 into 0.5. So, this will become 100, and PAB max. So, you have let us say 100 atoms. So, 100 atoms means 10 row. So, 10 this way, 10 this way. So, you will have 100 in place. So, total number of 200 bonds that you will have. So, total number of 10 horizontal bonds, 10 vertical bonds, 100 horizontal, 100 vertical bonds. As a result, PAB max is 200. So, this small s in this case will be equal to 100 minus 100 divided by 200 minus 100. This will be equal to 0. So, which means it is completely random solid solution, disordered solid solution. So, this means disordered. However, if you have S to be equal to, let us say, PAB observed, which is equal to so case 2, let us say. So, if PAB observed is, let us say, 130, PAB random that we have worked out is 100, and PAB max, so this is random, this is max, is 200. In such a case, S would be equal to 130 minus 100 divided by 200 minus 100. This would be 0.30. So, this will have certain degree of ordering. It is complete, so it is partial ordering. Which is called as short range ordering. And this would look something like, if you have so in certain regions you will have ordering. Here also, let us say, you have ordering, but in other regions you have disordering. So, they do cluster, tend to form. So, you can see that certain regions are ordered, certain other regions are disordered, or you can say certain regions are perfectly ordered. So, this is short range order, but other regions are random, so clustered there. So, this is sort of example of partial or short range ordering. And of course, perfect ordering will have case 3, perfect ordering or long range, you can say long range. In that case, PAB observed would be same as PAB max. So, S would be equal to PAB max minus PAB random divided by PAB max minus PAB random, and this will be equal to 1. So, for a long range ordered solid solution, S will be equal to 1. For a completely random solid solution, SAB equal to 0, and for short range ordering it would be intermediate values. So, these are the mathematical tools to define the ordering disordering. However, in the context of thermodynamics, basically what it means is that ordered structure defines low entropy of mixing, and disordered structure has high entropy of mixing. So, if you just consider the entropy, because disordered phase will have higher configurational entropy, as a result higher entropy of mixing. So, what is that now? But in reality what is observed is that generally at high temperature your disordered phase is stable, whereas low temperature ordered phase is stable. And we know that delta G, delta H mix minus T delta S mix. So, as far as the comparison of two phases is concerned, T delta S mix term is surely higher for the disordered phase. However, this enthalpy term is also is an important factor. So, it is the relative competition between delta H mix and T delta S mix which governs at which temperature which phase is stable. So, as far as ordered phase is concerned, for them they are stable generally at low temperature, and for them minus T delta S mix is not. So, I can say that plus delta T not large, but delta H mix is less than 0. So, it typically happens at lower temperatures when delta H mix is lower, T delta S mix is not large, and in comparison to disordered phase, delta H mix term of this phase dominates. As a result, they are more stable, whereas disordered phase high temperature, T delta S mix larger, as a result entropy term is bigger, but delta H mix is relatively it's higher than delta H mix of ordered. So, it generally happens at high temperature. So, it is the competition between delta H mix and T delta S mix terms of two phases which dictate which term will be stable. So, in general, for example, CuAl at high temperature, it is the BCC phase which is stable, disordered, and at low temperature it is the simple cubic phase which is stable, which is ordered. And there are various other systems in which these phases exist, for example, copper gold system and various other systems in which ordering disordering happens, and which is determined by competition of enthalpy of mixing and entropy of mixing. So, we will finish here this lecture in which we have discovered, we have talked about the real solutions in which enthalpy and entropy term can be very different from the substitution from the ideal and regular solutions, which did not consider the factors such as size difference, valence difference, electronegativity difference, strain difference, and so on and so forth. So, we will take up in the next class some other issues related to the real solutions. Thank you.